derived from a coin flip, maps the outcomes of a coin flip to some numbers, to a random variable. And so we could say that the random variable is equal to 1, or let's say it's equal to 0 if we get tails on my coin. And let's say if it's equal to 1 if I get heads on my coin. Now, the one thing that this random variable definition is not doing for us so far is telling us the probability of getting a random variable to be 0 or 1. To get that information, we need something called a probability distribution. Probability distribution for this random variable. Essentially tells us the probability that we get any one of these outcomes. Now, is this a discrete or a continuous random variable? Well, the outcomes here are distinct, they are countable, you could list them. This is definitely a discrete random variable, so we will construct, or we will be taking a look at discrete probability distribution. Discrete probability distribution. So let's say someone says, okay, I've defined this random variable in some way for a given coin, and I'm going to give you the probability distribution. So they come here and they start drawing this probability distribution. And most probability distributions, they tend to be depicted visually. And so here in the horizontal axis, I will plot all of the possible outcomes. We can do this as kind of the outcomes from a random variable x. So the outcomes are either, I'm going to get a 0 or 1. So 0 or 1. There's no other outcomes. I guess you could list other outcomes and just say they have a 0 probability of happening. These are the ones that can actually happen. And then here on the vertical axis, I'll plot the probability of getting any one of those outcomes. And so the person tells you, okay, the probability of getting a 0 is 50%. 50%, so they draw a little bar here. It's a histogram, a bar chart. So this goes right up to 50%, which I'll draw as a decimal, 0.5. And they tell you the probability of getting a 1, of the random variable becoming a 1, is 60%. 60%. Right, just like that. 60.
Okay, I'm just stopping the video, just so you remember, in this discrete probability, this is not necessarily the same as the flipping the coins in the classical method where you know it's equally distributed. Okay, just looking at a distribution for this particular example, 0 being tails, 1 being heads. There's a 50% chance of getting 0 or tails, a 60% chance of getting heads. These two bars represent the probability distribution. So similar to the frequency distribution, which we discussed in the earlier chapters.
60% or 0.6. Now my question to you, and I know you're just starting to be exposed to probability distributions, but based on what you know about probability, is this a legitimate probability distribution? Let's think about what the probability of of getting any one of these outcomes. Let's think about the probability that a random variable is equal to 0, or we're doing a union here, not an and, or the probability that our random variable is equal to 1. These are all the possible outcomes. We're essentially saying, what's the probability that we get one of the possible outcomes for our random variable? Well, over here, we would just add the two probabilities. So the probability of this one right over here is 0.5, and then we're taking a union. So, and these are mutually exclusive events, so we can just add the two together. And then we have the probability of getting a 1. The probability of getting a 1 is 0.6. Actually, let me do that in a different blue. 0.6. This strangely adds up to 1.1. Somehow saying that you have 110% probability of getting any of the possible outcomes. This makes absolutely no sense. You cannot have a greater than 100% chance of having any one of the outcomes.
Okay, so can someone explain why it cannot be 1.1 or 110%? Well, remember, go back to the other probability. Even though this is discrete, it's still heads or tails. And it's still 50% you get heads and 50% that you got tails. Even if somebody told you it was 60% for heads and 50% for tails, when he's doing the equation here, x equals 0, union with x equals 1 is 0.5 plus 0.6 is 1.1. It cannot happen because no probabilities can go over the number 1.
If looking at all of the outcomes from a random variable, it should add up to 100%. So you point this out to the gentleman who's trying to tell you that this coin is defined in this way, the probabilities are, and he says, oh, yes, I made a mistake. That was not the probability distribution. This right over here is not 0.5, 0.5. Clear it. Actually, let me clear this and redraw it. So he realizes that this was actually 0.4. 0.4. And now my question again to you is does this at least look like a legitimate probability distribution? Well, sure. The sums of the exclusive outcomes that this random variable can take on now equal to 1, 0.6, 0.4. Now the last thing I'll ask you, given what you know about this random variable, it's clearly an unfair coin. Are you more likely to get heads or tails? Oh, the random variable, you're clearly more likely to get an outcome of 1. If you look at the definition of a random variable, the random variable will be 1 when your coin is heads. So it's clearly somehow the coin is weighted a little bit more probable to having heads. So I'll leave you there. In the next few videos, we'll study more and more.
Okay, does everybody understand that? The conclusion that you can draw from these coins? Anybody? Anybody watching? Why can you say that it's a weighted coin? No one? No one understands? Correct. Correct. Correct, Wellington. Because this is somebody telling you, I have a coin. I'm going to flip this coin. You know. And we've talked about it. There's only 2 outcomes, heads or tails. And remember, in theoretical probability, it's only 50-50 chance. So if this person says, well, heads are 60% and tails are 40%, yes, it does add up to 100%. However, you already know that the coin cannot add up. It cannot be one side or the other more heavy than the other. So you know that the coin is weighted. So is that clear for everybody? Does anybody have a question about that? No questions. Okay. Let's finish that up.
Which is really the core of probability, and we see it becomes a very helpful thing when we start to study inferential statistics.
Okay, we'll stop that.
We've already spent some time.
Okay, I'm going to show you the show you the next video that we didn't see. Okay. Very dramatic music.
Hello, welcome. This video is an introduction
Sorry.
to probability distributions. A probability distribution is a table or equation that determines the probability or odds for all possible future outcomes. The most simple way of explaining probability distributions is to show an example using men's height. Let's say that the average height for men is 5 feet 9 inches. Probably it isn't, but for this example, we are pretending that it is. If I measure men's height and make a graph of the results rounded to the nearest inch, we see a large spike at 5 feet 9 inches that declines as we move away from 5 feet 9 inches. The height that occurs most is 5 feet 9, and the next most common heights would be the closest heights to 5'9", meaning that the next most common heights would be 5 feet 8 inches.
Okay, can someone tell me what the standard deviation is here? What's the mean? What's the centermost bar? 5'9". Okay. What's the standard deviation here? You know what the mean is? Look at the bars. How far do you have to go, or how much distance is there between 5'9" and 5'10"? 1 inch. Okay, between 5'9" and 5'8". 1 inch. Okay, it's not 0.1, it's 1 inch. Okay. So when you get data like this, always be looking at it to see, now this one looks like it is somewhat normally distributed, which it is. Okay. You look at that, you look at the curve, you look at the mean, and you look at the standard deviation. So you already know that you already have this information. So it's really important when you look at this to get that information out of the graph.
And 5 feet 10 inches. And the frequency of occurrence would decline in a stair-step manner, moving away from 5 feet 9. If I round the measurements to the nearest 1/10 inch, we again would see a large spike at 5'9" that declines in a stair-step manner as we move away from 5'9". We can use these graphs to make inferences about what will happen in the future. For instance, the graph shows us that there's a 50% chance the male child will grow up to be above 5 foot 9 inches, and a 50% chance that he will grow to a height below that. One can calculate out the probability or odds that a child will be between 5 foot 8 inches and 5 foot 10 inches, or between 5'7" and 5'11", or between any two heights. We could also calculate out the probability or odds that a male will grow above or below a certain height. In all three examples, we rounded the data, which means when we graphed the results, the graph formed a histogram around the average of the height. We can increase the resolution of the data by rounding to the nearest 1/100th of an inch, 1,000th of an inch, and so forth. As we increase the resolution, the graph will approach a normal distribution L-shaped graph, which brings us to continuous graphs and the central limit theorem. Because someone's height is a random number, the central limit theorem tells us that if we make a graph of men's height and we graph enough data, the graph should form a normal distribution L-shaped graph. A continuous distribution, such as the normal distribution, determines the probability for all possible outcomes. The most common continuous distribution is the normal distribution, which is the standard Bell graph. But there are other distributions as well, such as a t-distribution, which we will cover in later videos. Like a histogram, we can use a continuous distribution to determine the probability or odds of possible future outcomes, such as the odds of a man being above or below a certain height or between two heights. There are advantages to using a continuous distribution graph to determine future probability over using a histogram. However, both have their strengths and weaknesses. The discrete histogram and the continuous distribution, such as the normal distribution, are used along with statistical tools to model future outcome and probability of occurrence. We can use this type of modeling to determine probability of future returns of an asset.
Okay, so I don't know whether people have heard of this, the Monte Carlo simulation. It's actually used in business. Has anybody heard of this simulation? You can run this on a computer. No? Okay. Anybody heard of it? No. All right. I'm not sure whether you can do it in Excel or not. So what a Monte Carlo simulation will do, it'll show you in the video. But you can simulate how a stock or a bond or whatever you're investing may look like in terms of its distribution.
We can create a histogram of the periodic daily returns for that asset and use it to make inferences about future asset returns. In other words, we can use the histogram to determine the probability or odds of what will happen in the future. Like Ment's height, asset returns are also a random number. In other words, an asset such as a stock can increase or decrease any percentage. Therefore, the central limit theorem states that if we graph the periodic returns of an asset and we graph enough returns, that graph will also form a normal distribution bell-shaped graph. The normal distribution follows the empirical rule, meaning that 68% of the data will fall within one standard deviation of the mean, and 95% of the data will fall within two standard deviations of the mean. For a complete understanding of standard deviation, please see my three-part series on the standard deviation. So that is a basic introduction to probability distribution.
Okay. Oh, sorry.
Hi, I'm Dr. Nick.
Okay, I'm just going to go back to the PowerPoint. I think that's where we were. So it's kind of a review, but I hope you're seeing how that all the concepts that we are talking about are related to each other. Okay, so as discussed in the first video about random variables, so there are two types of random variables. So what are you saying there? I can't. Just to be clear, is like in stock, you look at before to see how much in certain time increases or decreases, and regarding that, you make an assumption. You look at the data, and you record the data to try and predict what will happen in the future. Yes. Now, we haven't talked about this, but when you make predictions, I mentioned it briefly, is that well, from a statistical perspective, you want to have a very large sample size, okay, in order to make a prediction. You don't want a sample size of, oh, let's just look at last week. I think I had mentioned this. It's like you want to look at the data for the last 5 years, because that's going to, think about it. You want to have your data resemble a standard normal curve, a bell curve. That way you can make a prediction much more accurately than if you had less of a sample size. Okay, is that understandable? Okay, so we did look at this. We'll just go over it a bit more. So the discrete random variables, one which may take only a countable number of distinct values, such as 0, 1, 2, 3, 4, so on. Discrete random variables are usually, but not necessarily, counts. And we looked at that. A count, it's just a frequency, period. You're counting. If a random variable can take only a finite number of distinct values, then it must be discrete. So examples include the number of children in the family, Friday night attendance at a cinema, the number of patients in the doctor's office, surgery, the number of defective light bulbs in a box of 10. The probability distribution of the discrete random variable is a list of the probabilities associated with each of its possible values. And it is sometimes called the probability function or the probability mass function. Don't worry about the names. So the discrete random variable can assume only certain clearly separated values. It is usually the result of counting sight. So think about counting as just frequencies. The continuous random variable can assume infinite number of values within a given range. It is usually the result of some type of measurement. We're measuring. So the example, the length of each song on the latest Tim McGraw album. You're measuring the time. Second one, the weight of each student in the class. You are measuring the weight. The temperature outside as you're reading this book. So the amount of money earned by each of the more than 750 players currently on Major League Baseball. So does anybody not understand the differences between continuous random variables and discrete random variables? Everybody's got it? Think of discrete as it's not entirely frequency, but it's close to frequency. And continuous is like, you know, for example, you're measuring time, or you're measuring weight, or you're measuring height. Okay, it's continuous. It's on a continuous scale. Okay. So this looks somewhat familiar. The mean, variance, and standard deviation of a discrete probability distribution. The mean is a typical value used to represent the central location of a probability distribution. No different when we look at the regular mean. The mean of a probability distribution is also referred to as its expected value. The formula we have is mu, which is the mean, the sum of x, the probability of x. The variance measures the amount of spread in the distribution, the same as it's always the variance is always measuring the spread. And how to compute it is you subtract the mean from each value and square this difference. You multiply each squared difference by its probability, sum the resulting products to arrive at the variance. And the standard deviation, same as before. The only difference here is you are multiplying each squared difference by its probability. Okay? And the sum of the result is that the variance. The standard deviation is found by taking the positive square root of the variance. This is the formula for the variance. Okay? I'm going to, I believe, have the video on this. Well, that's interesting. Sorry, I just got to check something here. Not sure why. Any questions so far? No questions, okay. Okay, sorry, I didn't have that video up. Okay.
The mean, variance, and standard deviation of a discrete probability distribution. For example, suppose a classroom is randomly selected at a state university. Researchers want to determine the probability that a student is taking exactly 4 classes. The data collected created the following discrete probability distribution. Using the discrete probability distribution, compute the mean, variance, and standard deviation. To compute the mean, variance, and standard deviation of a discrete probability distribution, we use the following formulas. The mean, also known as the expected value, is represented as mu, and that is equal to the sum of the quantity of each x value times its corresponding probability. The variance, which is represented as sigma squared, is equal to the sum of the x squared values times its corresponding probability minus the mean squared. The standard deviation which is equal to sigma, is found by taking the square root of the variance. So first, we are going to compute the mean. And the mean is found by taking each x times its corresponding probability and then summing them together. So our first x value was 3, and we're going to multiply that by its corresponding probability of 3 over 23, and that's equal to 0.3913. Our second.
Okay, I just want to remind people, we can't see the chart, but what do you mean by x, John? You're just figuring out the means here, okay, in the equation. Well, you already know 3, okay, is the mean. 3 over 23 is the probability, okay? That's what you get here, is the mean of a discrete population, okay? That's just it. That's the difference between taking the mean, variance, and standard deviation of a discrete probability distribution. In a regular one, you do not have this probability. Okay, so everybody should be aware of that because this is a discrete probability distribution, but you're still computing the mean.
The next value was 4, multiplied by its corresponding probability of 8 over 23, and that's equal to 1.3913. The next x was 5, and 5 times its corresponding probability of 9 over 23 is equal to 1.9565. And finally, our last x value of 6 times its corresponding probability of 3 over 23 is equal to 0.7.
Okay, John, I see what you're saying. She's saying x. Yeah, okay, this is, but they're all x. Okay, but they cannot be the same. She's saying the unknown then. Okay? All right.
7826. Our next step is to sum them. So now that we've multiplied each x times its corresponding probability, we're going to add them together. So we have 0.3913 plus 1.3913 plus 1.9565 plus 0.7826. And that sums to 4.5217. And so this tells us the average number of classes a student is taking is 4.5 classes. To compute the variance, again, the notation for the variance is sigma squared. We're going to sum the squared x values times its corresponding probability minus the mean squared. So again, we're going to square each x, multiply it by its corresponding probability, add them together, and then subtract out the mean squared. So our first x value was 3. So we're going to take 3 squared, multiply it by its corresponding probability of 3 over 23. And that's equal to 1.1739. Our next x value was 4. So 4 squared times.
I just want to make sure, is everybody on, is there anybody that does not understand where she's getting the numbers from? Everybody understands where it's coming from? Okay. All right, good.
its corresponding probability of 8 over 23 is equal to 5.5652. Our next x was 5. So 5 squared times its corresponding probability of 9 over 23 is equal to 9.7826. And finally, our last x of 6, so 6 squared times its corresponding probability of 3 over 23 is equal to 4.6957. So now that we've done this piece, we're going to sum them. So we're going to add them all together. So I have 1.1739 plus 5.5652 plus 9.7826 plus 4.6957. And once I add all of them together, I end up with 21.2174. So now that I've done this first part, I'm now going to subtract out the mean squared. So 21.2174 minus the mean, and the mean from the previous screen was 4.5217. So we square that. And once we perform the math, we end up with 0.7716. So the variance is 0.7716. Finally, to compute the standard deviation, the notation for the standard deviation is simply sigma, which is found by taking the square root of the variance. We found the variance to be 0.7716. So once we take the square root of that, we end up with 0.878. So the standard deviation is 0.878.
Okay, so does everybody understand the steps that you went through to get the mean, the variance, and the standard deviation? No questions? Okay, good. Remember, what you're doing here is you are multiplying the numbers recorded by the probabilities, okay? And then you're doing exactly the same steps in figuring out the variance and figuring out the standard deviation and figuring out the mean, except you now have probabilities included. Okay? All right. We'll go back to the PowerPoint. Okay, so all right, so here's an example. John, I don't know whether we went through this before, but anyways. John Ragsdale sells new cars for Pelican Ford. John usually sells the largest number of cars on Saturday. Yeah, we did this, but we'll go over it again. He has developed the following probability distribution for the number of cars he expects to sell together Saturday. So, as you point out, John, this is X. We know what X is. Okay, so we go from 0 to 4, the max. Here's the probability of selling 0, 10%, of 1 car, 20%, 2 cars, 30, 3 cars, 30, 4 cars, 10%. It must always add up to 1 or 100%. Formula for the mean, you have the X multiplied by the probability plus the other observed values multiplied by their respective probabilities, and we get 2.1. So if you look at this chart here, here's the number of cars sold. Here's the probabilities of selling this number of cars. We end up with these numbers when we multiply the X times the probability of X and add them up. We have the mean equals 2.10, and the variance, we have the mean, the observed X minus the mean, we square it. So in the first case, we have 0 cars sold. Probability is 10%. 0 minus 2.1, which is the mean. Square that, we get 0.41. Okay. We multiply by the probability, you get 0.441. Okay, we add this up. The variance, sigma squared, equals 1.290. And remember, the standard deviation is the square root of the variance. So the square root of 1.290 equals 1.136. Is there any questions about this example? Does everybody understand this? Anybody not understand the procedure? Okay, so remember, this is the probability because you are doing the mean and standard deviation of a probability distribution. All right. Okay. Now this part may get a little hairy because a lot of people don't understand it, but it is logical. So we're going to talk about the binomial probability distribution. Can someone think of what it means if it's a binomial probability distribution? Can everybody see the PowerPoint? Can everybody see this? There are only two possible outcomes for using I in front of the number. So only two possible, that's where we get a binomial probability distribution. The outcomes are mutually exclusive. The random variable is the result of the counts. And each trial is independent of any other trial. So there's no dependence on here. This is the binomial probability formula. Probability of x equals c n to x. This is like your original number going to whatever number you measure times pi to the x exponent times 1 minus pi to the nth exponent minus x. So c is your combination, n is the number of trials, x is the random variable defined as the number of successes, pi is the probability of success on each trial. The mean is equal to n times pi. Remember, you don't have to memorize these formulas, they're all there. Variance of binomial distribution, sigma squared equals n times pi times 1 minus pi. And this is our example. There are 5 flights daily from Pittsburgh via U.S. Airways into the Bradford, Pennsylvania Regional Airport. Suppose the probability that any flight arrives late is 0.20. So we know what the probability is, 0.20. The question is, what is the probability that none of the flights are late? Okay, so let's figure out what average number of late flights. What is the variance of the number of late flights? So here's the formula. Substitute in the numbers. So we have 1 for the count times the pi times 1 minus pi equals 0.3277. So that is the probability of figuring out the number of flights. Figuring out the mean, u equals n times pi. Okay, so the mean is 5 times 0.2. This is where the probability is. We have 1. Sigma squared equals n times pi, 1 times 1 minus pi, 5 times 0.20 times 1 minus 0.20. We get 5 times 0.2 times 0.8 equals 0.8. I know it looks complicated because of the formula, but basically you're just plugging in the values. So what is the probability that none of the flights are late today? The probability is 0.80 or 80%. And I will mention this to you. If you have in your evaluations or even in the homework, if you have a question such as this, what is the probability that none of the flights are late today? When you come up with your answer, I want you to put it in sentence form. I don't want a number. Okay? So I don't know whether people have previously done word problems, but it's important that you answer the question in the form of a sentence. Okay? So I'm going to, let's see, the video on this. Okay. All right.
For this video, what we'll do is we're going to find the mean, the variance, and the standard deviation for a binomial probability distribution. The mean for a binomial distribution is found by taking n, which is the number of trials that are done in your binomial experiment, times the probability.
Okay, so just for notation sense and for your understanding, n is a number of trials. How many times was this done? Okay, that's easy enough.
Probability of success C. Remember that you must always use mu when you're talking about the mean of a probability distribution because you're talking about the entire population. And so it's a population parameter, so we would use mu. The variance is sigma squared, is the notation that you would use to represent the variance. And for a binomial distribution, this is the easiest hand calculation out of all of the types of variance. And all you have to do is n times p times q, where n is the number of trials, p is the probability of success, and q is the probability of failure. The standard deviation is always found by taking the square root of the variance. So you would just take the square root of n times p times q. Make sure that anytime you are dealing with the binomial distribution that you do use the correct notation. These are parameters because they are talking about the population distribution.
Okay, so remember, can someone refresh everybody's memory what a parameter is? What's a parameter? Nobody remembers. What's a statistic? Look at the mean calculation. Mu equals n times p. What is the mu equal? The mirror. What does the mu mean? Not numerical. What is mu? It's the population mean. A population. X bar is the statistic mean or the sample mean. Okay? So, as said in the video, because it's a binomial distribution, it's already a population. So you use the population notation, mu. Okay? Just so you know the differences.
So the case that we have here, a die is rolled 21 times. Find the mean, the standard deviation, the variance, and if a success is considered rolling a 5. I'm also going to discuss with you what.
Okay, I'm just going to mention this because this is technically a word problem. And in the word problem, what you want to do is you want to break it down and you want to find what they're asking for. Okay? So, what is it that they're asking for in this question? Anyone? that it? Just the mean, Wellington? See, you're not reading it. Read the problem. Finding the mean. What else? Right. When you look at the problem, you have to look at the whole problem. You have to find out what is it that's being asked here. You're looking at this and you see that the die is rolled 21 times. Okay? That's the condition. So you know. Okay? And further to the condition is if a success is considered rolling a 5. So that way you can figure out the probabilities. So I want you to approach, because you're going to only really in the future get word problems. So you should be able to actually dissect the sentences to understand what you have and what the unknown is and what you have to find. Okay? It's a very important concept.
Would be considered an unusual event. Okay, so let's find the mean first. So the mean is equal to n where, let me write down all the important information first, sorry. So before you start, you always want to find your important information. N, remember, is the number of trials that you have, so N is going to be 21. P is going to be the probability of success, and in this case, the probability of rolling a 5 is always 1 out of 6. And the probability of failure, which is Q, is always 1 minus P. And in this case, it would be 5/6. Okay, once you figure out your important information, then you would go through and find your mean.
Okay. So I'm just going to repeat it, and maybe the language I used was not understandable. You want to write down the information you know. Okay, we know n is 21. It's 21 times. The probability of rolling a 5 in a one-sided die, in a die, what is it? There's only 1 5, right? It's 1/6 because there's only 1 5, and the probability of rolling a 5 is 1 in 6. And Q is defined equals 1 minus the probability, or 1 minus 1/6 equals 5/6. So you've already found N, P, and Q. All right? So this is how you should be approaching these word problems.
Your variance and your standard deviation. So the mean is always going to be N times P. So we would take 21 times 1/6. So when you do this and you plug it in, you end up with 3.5. So the average roll of a die 21 times, or out of 21 times, we would expect to see 3.
I know this is impossible because on a die you cannot get 3.5. This is just done for mathematical purposes. You do not round this down or you do not round this up. Okay? This is just a number that you're exactly. So you're just saying this is a number calculated. It's not possible. For this example, you use this number.
0.55 out of 21 rolls. We know we can't ever get this. That's the one thing about the mean, is the mean does not have to be possible. It is impossible for us to actually roll 3.5, but if we were to do this infinitely many times, the average number that we would see is 3.55 out of 21. The next thing that we're going to find is the variance. And the variance, remember, is N times P times Q. So you would take 21 times 1/6 times 5/6. And I am going to round this one. This one does round to 2.916 repeated. So you could put a repeated around it, or you could say 2.9.
Is there anybody not familiar with this bar over the 6? Does anybody not know what that represents? Everybody knows? Well, what does it mean, John? When the bar is over the 6, what does that mean? It repeats 6 over and over, correct. Okay, so for everybody that is not familiar with that, the bar over a number means that that number is repeated, so you don't have to write it out a million times. You just put in the single number with a bar over.
17. It is best to not round for the next calculation. It's best to just put into your calculator the square root of your answer, just because of the fact that if you do round it, your standard deviation may be off slightly. So the standard deviation, remember, is found by doing the square root of the variance. So we can just take the square root of 21 times 1/6 times 5/6. And in your calculator, what you would do is just do the square root of your answer. So this is approximately 1.708 to 3 decimal places. So out of 21 times.
Just a note, if you're doing something like this, if you have a problem like this, please do it to 3 decimal points. Okay? Thank you.
Times. Okay, so if a die is rolled 21 times, out of 21 times, we would expect to see 3.55s rolled on average.
Okay, is there anybody that doesn't see that? That's answering the question here. Okay, what is the mean? Okay, so out of the 21 times you rolled the dice, you would expect to see 3.55s rolled on average. You figure that out up here with the mu.
Okay, and the standard deviation of 1.708. Okay, with this, you can also find unusual events to see what would be unusual. Unusual events are more than 2 standard deviations. Above or below the mean. Okay, so if you were asked to unusual events for this, what you would do is you would just take your mean and you would do plus or minus 2 times the standard deviation. So let's look at both of those. If I do my mean, which is 3.5, minus 2 times 1.708, we get 0.084. And if we do 3.5 plus 2 times 1.708, we get 6.916. So it would be unusual out of 21 rolls. So
actually, in this case, it would be impossible, right? Because we're talking about rolling a die. You cannot get 0.084. You cannot get 6.916. But in other cases, you may get that.
it would be unusual to get 0 5s or 7 or more 5s. Okay. So really we would expect to see 1, 2, 3, 4, 5, or 6. Those would all be considered normal. Anything on the outside of that becomes unusual, and while it could happen, it's just not as likely to happen. So as a recap, remember to find the mean of a binomial distribution. This only works for binomial distributions. You take the number of trials times the probability of success The variance is the number of trials times the probability of success times the probability of failure, and the standard deviation is just the square root variance. As always, thanks for watching. Please continue to check out all of my other video content, and if you have any suggestions, please let me know.
Okay. All right. So we're going to do another example. And I have no idea what a worm gear is, so don't ask me. 5% of the worm gears produced by an automatic high-speed Carter Bell machine are defective. So what is the probability that out of 6 gears selected at random, none will be defective? Exactly 1, exactly 2, exactly 3, exactly 4, exactly 5, and exactly 6 out of 6. So in this chart here, table 6.2 or 6-2, binomial probabilities for n equals 6 and select values of pi. So here we have the 6 gears, okay? And these are the probabilities across the top. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, all right? And the shapes for the varying constants. So the successes, pi equals 0.05. Okay, here's 0.1, 2, 0.5, and 0.7. These are all successes. On the bottom, we measure the successes. And this is the shapes for the varying n, when n equals 7, n equals 12, n equals 20, n equals 40. Okay. The one at the end is starting to look like a normal distribution. The 3 other distributions are skewed. Okay. Skewed to the left. And oops, sorry. Okay. So here are the probabilities, sorry, confined. So if you have a problem like this, the expectation is you would draw a table. Okay, you don't necessarily have to draw the graphs to represent it, but drawing a table of the probabilities, so it makes it easier for someone to review exactly what they would be. Okay? Okay, so cumulative binomial probability. Just hold on, I'm trying to get the video here. Okay, sorry. Okay. And my E went over. So, cumulative, what does cumulative mean? Anybody? No one knows what the word cumulative means. What do you think it means? Have you heard it before? The total, right, Amir? It's the cumulative, the accumulation of everything. So it's your total. So here we have a study by the Ministry of Transportation concluded that 76.2% of front seat occupants used seat belts. And a sample of 12 vehicles selected. What is the probability the front seat occupants, exactly 7 of the 12 vehicles, are wearing seat belts? So here we have the probability of x equals 7, n equals 12. The probability equals 0.762. Okay? So all the numbers are known here. We have the 7 for x. We have 12 for our n, the number of trials. And our probability is 76.2 or 0.762. Remember, this is a percentage, so it'll be written as 0.762. So we have 0.762 to the 7th power times 1 minus 762, 12 minus 7 to the power. We have 792 times 0.149171 times 0.000764 equals 0.0902. That is for exactly 7 of the 12 vehicles. People in the front seat are wearing a seat belt, which is very small. It's 9.02%. And the second question is asking, what is the probability the front seat occupants in at least 7 of the 12 vehicles are wearing? You have to pay attention to what the question is asking and the words they are using. And I think I mentioned this way back at the beginning of the class, that if English is not your first language, please have a dictionary available when you are doing the evaluations, the test and the exam. Okay? How do you get 792? It's from this formula here. 762 to the 7th power times 1 minus 0.762. How do you get 762? Transportation included, that's 76.2%. What does 76.2% equal in terms of a decimal? John? What equals a decimal? What's its equivalent decimal? Exactly. That's where the 762 comes from. Okay, so the second question is, what is the probability of front seat occupants in at least 7? Okay, so here you go, x is greater than or equal to 7. These numbers remain the same. But the probability is going to be different because x equals 7, x equals 8, x equals 9, x equals 10, x equals 11, and x equals 12. So we're going to have all these and add them up, okay, and end up with 95.62% or 0.9562 probability of at least 7 of the 12 vehicles in the front seat occupants, and at least 7 of the 12 vehicles are wearing seat belts. Okay, so there's a higher probability that at least 7 of the 12 vehicles, the people in the front, are wearing seat belts. Okay, pay attention to these signs. Excuse me. X equals 7 here. X is greater than or equal to 7, so you have to include the 7, 8, 9, 10, 11, and 12 of the vehicles because it's asking what in at least. All right? Any questions about that? All right, let's see the video. Okay. Okay. The most important thing is you have to understand the question. So you have to read it carefully. Okay? Even if you have to read it 3 or 4 times, you have to know what you have available and what you have to find.
This is the star of his high school's basketball team. Opposing teams foul him often, but he makes his free throws 88% of the time. Marcus takes 6 free throws in one game. There's a probability that he makes at least 2 of the attempts. You may assume the attempts are independent of each other. All right, so it's a probability question, and they're asking us for the probability he makes at least 2 of his 6 attempted free throws. So whenever we see a probability question, we have to ask what type of probability is it. If there is more than one trial or more than one selection, we want to think of multiplication rule or perhaps binomial probability, at least in the context of the topics we've learned in this course so far. So one rule of thumb is you should probably consider that it's binomial probability if not all of the attempts are turning out the same way. So for example, if they said he's taking 6 attempts and he misses all of them, you can do that with multiplication rule of probability pretty easily. If he says they're taking 6 attempts and he makes all of them, again, somebody's taking 6 shots and he makes all of them, then that's multiplication rule of probability, or at least multiplication rule of probability can be used to solve it quite easily. However, if they say that he's taking 6 shots and he's only going to make 2 or more, or 3 out of 6, etc., in other words, if they're not all turning out necessarily the same, then at that point you should probably consider using binomial probability.
Okay, so that is the first important thing when you're reading the problem. If Marcus takes 6 free throws in one game, what is the probability he makes at least 2? So either he misses or he hits the shot. Only 2 outcomes are possible. He makes it or he doesn't make it. As mentioned, if he misses them all, you can use the multiplication rule. If he gets them all, you can again use the multiplication rule. If you have a problem like this, where it's either or, then you know it's a binomial probability question. Okay?
And all you have to do is go through the binomial probability checklist to see if it is a binomial experiment. So first thing we'd say is, can we express a random variable that counts the number of successes here? Sure, I think we can say that x here would be the number of attempts that he makes, or the number of times the ball goes into the basket successfully. So x would be equal to 2 or more, because at least 2 means 2 or more. If I said to you, you need at least a C to pass this course, it means a C or higher. So at least 2 means 2 or more, or 2 or higher. And 2 or more in this case actually means what? 2, 3, 4, 5, right? So it would be basically 2, 3, 4, 5, or 6.
Okay, so again, look at the language carefully in the question. He makes at least 2 of the attempts. That's the least. But he could make more. So he could make, as shown here, 2, 3, 4, 5, or 6. Does anybody not understand that? Because the language is very important for you to look at and understand what they're asking. Any questions? No questions? Okay.
Attempts going in. Okay. Do we have a fixed number of trials? Absolutely. He's taking 6 shots, so we know that it's clearly 6 attempts. Do we have a probability of success? Does it remain constant from trial to trial? I think it does. We say there's an 88% chance of success, so 0.88 for the probability of success. That means the complement is just 0.12 or 12%. How do we get that? We just do 1 minus the 0.88, right? And that will give us our 0.12. So the probability of failure, or Q in this case, is 1 minus probability of success. All right, very good. Now,
okay, so remember, P is success, the probability of, in this case, making his free throws. Q is the failures. And using the complementary rule, you subtract 0.88 from 1 and get 0.12, which is his failures. This is the binomial. Remember, it's either or.
now, we also have to make sure the trials are independent of each other, but they did tell us that in the problem, so we don't have to worry about that. Okay, good. So we have now an approach that will work, binomial probability. The problem is that this problem would require us to calculate all of these probabilities. We'd have to do probability that's 2 plus the probability that it's 3 plus ... all the way up to the probability that it's 6. If you count that out, that's 1, 2, 3, 4, 5 different probabilities that all have to be worked out. That's a little time consuming. We don't want to have to do it that way. But if we went ahead and said, hey, look, probability that it's 0 plus the probability that it's 1 plus the probability that it's 2 all the way up to 6, that has to add up to 1. Has to, because we've covered all the cases that are possible. When we take 6 shots, he either makes no shots, right? Either makes 1 shot, 2 shots, 3 shots, so on and so forth, right? So we've covered all the possible cases, so we must have all the probabilities, so we must have a total probability of 1 for this equation. Now, if that's the case, and we want this portion, that's the portion we're trying to solve for, then we can just subtract this portion away from 1. In other words, if I do minus the probability that it's 0, minus the probability that it's 1, I should end up getting my solution, right? Because then I'll be left with the part that I want. So the way to solve this, the way to solve the probability that x is greater than or equal to 2, right, 2 or more, is equal to 1 minus the probability of 0 minus the probability of 1. If I take those probabilities away from 1, I'll be left with the probabilities I want. Okay, and then you can do that with either a probability table like the binomial probability table, or you could do it by hand. I'm just going to do it by hand because it's not that hard to do by hand here. So probability that x is equal to 0, you actually don't need to use binomial probability for that, but we could fill it in if we wanted to. I'm going to skip doing that though because it'd just be time consuming. If you think about it, 0 means 0 successes, right? That means every attempt is a failure. Well, here's the chance that he fails to make his shots, so 0.12. If he's going to do that every time and the trials are independent of each other, like they said.
All right. There's questions about that. The probability of him not making any free throws. And as pointed out in the video, Q is total failure. Doesn't make any. So we know that P of 0 is 0.12. So you already have this information.
And this just has to be raised to the 6th power, and that is the probability of 0, right? That means he missed every shot. Each time he took one, the chance he would miss is 12%. If you raise that 12% to the 6th power, that's the chance he misses all of them. Okay, then we have to work out the probability of 1 success. So we use the binomial formula for that. So out of 6 attempts, we're going to choose 1 to be successful. The probability of a success is 0.88, right? We're going to raise that to the 1 power because he'll make 1 shot out of 6. But then he's going to miss the other 5, so the probability that he misses is 0.12, the leftover amount of probability. And out of 6 shots, if he only made 1, 5 of them will be left, and those 5 shots will be misses. So that's the equation that we need to plug into the calculator. So if we put all this in, we'll have our answer in the calculator. Let's go ahead and do that. It'll be 1 minus 0.12 raised to the 6th power minus 6 choose 1, which is just 6, but we can type it in 6. And in my calculator, I come over here and bring it up in that way. So 6 choose 1 times 0.88 to the 1 power. I don't have to put it to the 1 power, so I'm just going to leave that alone. And then times 0.12 to the 5th power. Press enter, and there's my answer. It's 0.99986, so on. So it doesn't work out to be exactly 100% because if we round off to 3 places, it's going to end up being basically 1. I'm going to go ahead and just rinse off to 4 decimal places. That way it'll be 0.9999, right? So the answer we get at the end is 0.9999. There's a 99.99% chance he makes at least 2 of his attempts.
Okay. Everybody understand that example that was used? All right. Okay. So, finding the mean and the standard deviation of a binomial distribution. So it's the same process we go through. And because the binomial distribution is so commonly used, statisticians went ahead and did all the grunt work to figure out nice, easy formulas for finding its mean, variance, and standard deviation. And the following results are what came out of it. If X is a binomial distribution with n trials, and the probability of success P on each trial, then the mean of X is mu equals n times P. The variance of X is sigma squared equals n times P times 1 minus P. And the standard deviation of X is sigma equals the square root of this NP times 1 minus p. Okay. Okay, show this one, and I just want to show you another slide. Okay.
We worked through the probability distribution for this random variable defined as number of free throws you make when taking 6 free throws, assuming you have a 70% free throw percentage. And I suggested, hey, why don't you visualize this, draw the graph this probability distribution, this binomial probability distribution. And when I thought about it, I said, well, I too would enjoy graphing it. I might as well do it together, because whenever you graph these things, it makes it very visual and kind of the shape of a binomial distribution like this. So let's do that. So let me move over to the right a little bit. I really just need to be able to keep track of these things right over here. So draw some lines. So let me, I would have just one line there, and another line here. And then we have the different percentages. So let's do that. The highest one is a little over 30%, 30%. Maybe we'll go as high as 40% here. 40%, and then this would be 20%. 20, that looks about halfway. 20%. This would be 10%. 10%. This would be 30%. 30%. And then in this axis, let's do the different values that the random variable could take on. The random variable taking on the value 0. The random variable taking on the value 1. 0, 1. The random variable taking on 2. 2, almost there. 3, and 4. 4, and then 5. 5, and finally 6. Taking x equals 6. Then 6, and now let's just graph all of these. So this first one, 0.1%, well, that's barely going to register on this graph right here, so I'll just kind of just give a little bit of a showing right over there. I'll only do it in that green color. So in that green color, we're going to have this a little bit of a showing. 1 is what kind of barely a showing, so maybe it shows up a little bit more. Let me draw it like that. That is 1% right over there. Now 2 is 6%, which on this scale would be about, it's about that high, like that. That is 2. That is 6% right there. X equaling 3, 18.5% shot of that happening. So 18.5 gets us right about, it's a hand-drawn chart, so, or histogram, so you have to bear with me. So it's roughly there. And then 4 was 32.4%. So that is up here. 32.4% is right, like that. Let me shade that in. 32.4%. And then 5 was 30.3%. 30.3% is slightly lower, just like that. And it looks like this. 30%. And finally, 6 is 11.8%. 11.8%. So really, this whole video was just an exercise in making a histogram. But it's useful because to actually visualize what the distribution looks like. What's really interesting is,
Okay, here's my question. You know what? I'm going to do a poll. And there's the question. Okay, so I sent a poll out, so if people that are here, can you respond to this? Does this resemble a normal distribution? Okay, there's still 7 people. Can you please respond? Does the graph look like a normal distribution? Oh dear. Hello, are you 7 people still awake? Can you please respond to the question? Does the graph look like a normal distribution? Well, I guess people don't want to respond. Okay. I'm not sure why you're not responding. Okay, though, anybody who said no, can you please say why it doesn't look like a normal distribution? It's a huge difference between numbers. Draw a line. Pretend you're drawing a line over this. Does it look like a normal curve? Doesn't matter what the differences are. Look at the curve. Imagine you're drawing a line to the top of the bars. Okay, Amir, I'm trying to understand what the differences do. If you draw a line from the top of each bar and go along, does it look like a normal distribution? What is it? Is it skewed to the left or the right? Anybody? Anybody that said yes? Why does it look like a normal distribution? Hello, is anybody out there? Can't really go on. It's skewed to the right. What does that mean, Wellington? I'm not sure what that means. Are you saying it looks like a standard normal curve or it doesn't look like a normal curve? Oh, yes, okay. You don't know what the mean and the standard deviation is. But if you draw that line, will it look like a normal curve? Why, Amir? Why doesn't it look like? Are you sure about that? Because remember what a normal curve is. The tallest in the middle of the data. And it goes down on each side. That's what's happening here? A little, it goes down a little farther on the right-hand side. But remember, pretend you're drawing a line from the top of the bars. It's centered. Okay, right, Siddhartha. Okay, if it's centered, what shape is it going to take? curve is centered, what shape does it usually take? Not exactly like, perfectly centered, but it's close. A bell curve, right? That's right. It's a bell curve. It's close to being a normal curve. So look at that. You can look at that in relation to a binomial distribution. Okay? So it too may take on a normal distribution curve. That's all I wanted you to be. You have to look at that carefully. All right.
Is to think about, well, how does this change as you change the free throw percentage, or as you change the number of shots you take? How does this change this binomial distribution? And you can do that on a spreadsheet and actually see how that all works out.
Okay. So I wanted to show you that because it means you can graph your distribution. Okay. Anyway, let's go back. Right, we saw that. Okay, the mean and the standard deviation of binomial distribution. So, example, suppose you flip a coin 100 times and let x be the number of heads, and then x has a binomial distribution with an n of 100 and p equals 0.5. Its mean is mu equals np equals 100 times 0.5 equals 50. 50 heads, which makes sense because if you flip a coin 100 times, you would expect to get 50 heads. The variance is sigma squared. We'll just substitute the numbers in here. 100 times 0.5 times 1 minus 0.5 equals 25, which is in square units, so you can interpret it. And the standard deviation is the square root of the variance, which is 5. That means when you flip a coin 100 times and you do that over and over, the average number of heads you'll get is 50. And you can expect that to vary by about 5 heads on average. So the formula for the mean of the binomial distribution has an intuitive meaning. The P in the formula represents the probability of success, yes. It also represents the proportion of successes that you can expect in an end trial. Therefore, the total number of successes you can expect, that is, the mean of x, is sigma squared equals np 1 minus p. And 1 minus p equals 0.5. The formula for variance is somewhat the only variability in the outcomes of each trial is between success with probability p and failure with probability 1 minus p, or q. Over n trials, the variance of the number of successes failures is measured by mu equals n times p. The standard deviation is the square root. Okay. And oh, not that one. And sorry, I gotta find, just looking for this, and I don't know where it is. Okay, sorry. Sorry, I'm trying to get the video.
Hi, for this video, what we're going to do.
Sorry, we already saw that video. My error. Okay. Okay, and we saw how to graph the binomial distributions. I don't know how I ended up out of order, but I did. Okay. So, back to this. Has anybody heard of a Poisson probability? Okay. No? All right. I guess it depends on the math that you had previously. So this is another type of probability distribution. The Poisson probability distribution describes a number of times some event occurs during a specified interval. The interval may be time, distance, area, or volume. The assumptions of the Poisson distribution: the probability is proportional to the length of the interval, so it becomes dependent on time. The intervals are independent. So, an example can be the number of misspelled words per page in a newspaper. You have a set, limited parameter. It's the newspaper. It's the pages, each page of the newspaper. Or the number of calls per hour received by Dyson Vacuum Cleaner Company. Very precise, very specific. The number of vehicles sold per day at Hyatt Buick GMC in Durham, North Carolina. That is extremely specific. We're talking about one car dealership in one town, in one state, in the country. This one's a little more general: the number of goals scored in a college soccer game. Okay, this is the formula. Probability of X, mu is the mean number of occurrences, successes. Remember that. Occurrences is equivalent to successes in a particular interval. E is the constant, 2.71828. Don't even bother asking. I don't even know this name of this. Base of Napierian logarithmic system. That's what somebody has computed. X is the number of occurrences, successes, and E of X is the probability for a specified value of X. The mean is mu equals the n, all right, times that probability there. Okay, so let's, this is not a probability that happens or occurs a lot. It's got to be, as you see, arbitrarily specified by somebody because they want to find something specific and what the distribution is for that specific question. All right.
Let's look at an introduction to the Poisson distribution, an important discrete probability distribution. Suppose we are counting the number of occurrences of an event, a given unit of time, or distance, or area, or volume. For example, we might be counting up the number of car accidents in a day in a city like Toronto, perhaps, or the number of dandelions in a square meter plot of land.
Okay, so again, this is a specific question, all right? What is happening? The number of car accidents in a day. Doesn't say where, doesn't say when. But you want to be specific as possible, okay? You know, in a day in Toronto between, well, whatever and whatever, 6 in the morning and 6 in the evening at some particular section or street or whatever, okay?
Then the number of events is going to be a random variable that may or may not have the Poisson distribution, depending on the specifics of the situation. But a Poisson random variable is a count of the number of occurrences of an event. I'm going to phrase the following in terms of time, but the same ideas hold if we are discussing distance or area or volume, etc. Suppose events are occurring independently. In other words, knowing when one event happens gives absolutely no information about when another event will occur. And the probability that an event occurs in a given length of time does not change through time. In other words, the theoretical rate at which the events are occurring does not change through time. A little more loosely, we might say that the events are occurring randomly and
Okay, so does everybody understand that? The probability that an event occurs in a given length of time does not change through time. That means you're measuring whatever the number of accidents at a particular section. They don't change through time. They don't, oh, they always occur at 4:56 and at 5:27 and 3:12. They do not. They are random and they are independent. Any questions about that? Okay, we'll carry on.
independently. If these conditions hold, then the random variable x, which represents the number of events in a fixed unit of time, is the Poisson distribution. Here's the probability mass function for the Poisson distribution, we'll use to calculate probabilities. Probability the random variable x takes on the value little x, you'll sometimes see written as p of little x, is equal to lambda to the x times e to the minus lambda over x factorial. E, lie, is an important mathematical constant, the base of natural logarithms. It is approximately 2.71828, but it is an irrational number that has infinite non-repeating decimal places. We've discussed factorials previously, but as a specific example of this x factorial, 5 factorial would be 5 times 4 times 3 times 2 times 1, and that would be 120.
I just want to make sure, has anybody who has not done anything with the term factorial before? Okay. Is anybody not familiar with the term factorial? Okay. Everybody seems to know that. That's great.
It's not a probability distribution until we say what values x can take on. Here the random variable is a count of the number of events in a given unit of time, and so it can take on any non-negative whole number value. So this probability mass function that we use to calculate probabilities for any value of little x that's 0, 1, 2, off to infinity. There is no upper bound on the value that x can take on. But depending on the situation, the probabilities eventually get tiny for large values of x. The mean of the Poisson distribution is lambda. So mu, the mean of the random variable x, is equal to lambda. So we could have used mu as our parameter, and some sources do that. But we often use lambda for the Poisson distribution. The variance of the Poisson distribution, which we'll label as sigma squared, is also equal to lambda. For the Poisson distribution, the mean and the variance are equal. Let's look at an example. Plutonium-239 is an isotope of plutonium that is used in nuclear weapons and reactors. 1 nanogram, or 1/1000th of a gram, of plutonium-239 will have an average of 2.3 radioactive decays per second. The number of decays in a given period will go to a very close approximation of Poisson distribution. We'd like to know, what is the probability that in a randomly selected 2-second period, there are exactly 3 radioactive decays? We let the random variable x represent the number of decays in a 2-second period. Lambda is the mean number of decays in that period. So here we have an average 2.3 radioactive decays per second. We're talking about a 2-second period. And so in that period, the mean number of occurrences, which is going to equal lambda, is going to be 2.3 times 2, which is 4.6. And so x has a Poisson distribution with lambda equal to 4.6. We want to find the probability that the random variable x takes on the value 3. And the Poisson probability mass function is lambda to the x times e to the minus lambda over x factorial. And here that's going to be 4.6 lambda raised to the 3rd power times e to the minus 4.6 divided by 3 factorial. If we work that out on a calculator or computer, we'd see that's equal to 0.163 when rounded to 3 decimal places. So that is the probability of getting exactly 3 radioactive decays in a 2-second period. If we were to calculate the probabilities for the different possible values of x and plot them, we get this. This is the probability distribution of the random variable x in this spot.
Okay. Does this look like a normal curve? Anybody say, well, do people think this looks like a normal curve? No one? No one that's left is a pod, John. A normal curve. What's a positive curve? Skewed to the left? How do you figure? How do you figure, Amir? Why is it skewed to the left? Remember, pretend to draw a line from the top of each of the bars and go across the left side. Okay, that means okay, I see what you're saying. Okay, no, you have to look at the curve as a whole. This curve also resembles a normal curve. So I want that to point that out to you so everybody is aware of that. Just continue.
A Poisson distribution with lambda equal to 4.6. The number we calculated, the probability that x takes on the value 3, is here. That's what we just calculated to be 0.163. We can see here that x takes on the possible values 0, 1, 2 on up. I've truncated the plot over here at 15, since the possible values go off to infinity, but the probabilities start getting very, very small. For a Poisson distribution, there is no upper bound on the values the random variable x can take on. For this distribution, the mean, mu, is equal to lambda, and that's 4.6 here. The variance is also equal to lambda, so that's also equal to 4.6. And if we wanted the standard deviation sigma, we'd simply take the square root of 4.6. If we look closely, we can see that there's a hint of right skewness in this distribution. The Poisson distribution has some right skewness, but it depends on the value of lambda. When lambda is large, the distribution will be close to symmetric. When lambda is close to 0, the right skewness can be pretty strong. Suppose we wanted a different probability. The probability there are no more than 3 radioactive decays. Here that's the red bit on the plot. We need to work out the probability of 0, of 1, of 2, and of 3 using the Poisson probability mass function and add them together. So let's go ahead and do that. Here we need to find the probability that the random variable x takes on a value less than or equal to 3, which is the sum of the probabilities of 0, 1, 2, and 3. We put these values of x into the Poisson probability mass function with a lambda of 4.6. When rounded to 3 decimal places, these probabilities work out to these 4 values, and they sum to 0.326. Working out probabilities like this can be a bit of a pain if there are a lot of values, so we often rely on software to carry out the calculations. There is an important relationship that sometimes helps us determine whether a random variable has a Poisson distribution. The binomial distribution tends toward the Poisson distribution as n tends to infinity, p tends to 0, and n times p stays constant. For us at the moment, the important bit is that the Poisson distribution with lambda equal to n times p from the binomial distribution closely approximates the binomial distribution if n is large and p is small. In fact, this is why the radioactive decays of plutonium has a Poisson distribution. Even for a tiny bit of plutonium, there are a very large number of atoms, and each one has a tiny probability of experiencing a radioactive decay in a 2-second period. So in the example we just worked through, it was in its underlying nature a binomial problem with a very large n and a very small p, and that's why the number of radioactive decays is very well approximated by the Poisson distribution. I have videos that explore this relationship in greater detail. Like many models in probability and statistics, the Poisson distribution is typically used as an approximation to the underlying reality. In most situations where we use the Poisson, we know that the Poisson distribution doesn't fit the scenario precisely, but we use it as an approximation, possibly a very good approximation. But it can be difficult to determine whether a random variable has a Poisson distribution to a reasonable approximation. So I'm going to look at a few examples and discuss some considerations in another video.
Okay, we'll stop there for today, but I have a question to ask, and I'm going to ask now, if you can see, I'll just go back to the PowerPoint. Okay, as you can see, we are on slide 13 of 16, which means we will probably complete this chapter on Tuesday. So my question will be, now I can't find it. Where is it? I want to ask people if I have a question. So since we'll be finished on Tuesday, this chapter, and remember that as at 5 o'clock today, the chapter 4 test is available up until Monday at 5. So the question to be, do you want to have, you don't want to have it, but we'll be finished chapter 5 on Tuesday. So I can have the 5 tests available that will go from Tuesday at 5 till Thursday at 5. Otherwise, I don't want to give you the test during the intercession week, which is the week after next. And so it would be available from the Monday to the Wednesday in the week that we come back. So I'm just going to put that down. And can please everybody, all 11 of you, answer. Before anybody says anything, let me ask the question here. Okay. Let's see. Okay. Next week is not the intercession week. Oops. Oh, it's the test, Amir, the test of the chapter. You know what? Let me just ask the poll. Okay, so I put up the poll. So can please everybody respond? Otherwise, I will just set it. And nobody's responding. You can't answer? Oh. Okay, let me clear it again. Sorry, everybody. Okay, I'm just going to stop.